Now there's this small section over here, which is the analysis to demonstrate the small dynamic range of inputs V1 when related to currents I1, I2, I3, and I4. So these are just there for you to do. This is the general differential amplifier equation. Where if you plot V1 versus, if you plot V1 if you were to plot V1 versus I1, you get a curve, something like this. And so this is I1 and I2, or IC1 and IC2. And to show that the clipping occurs at 4 VT. So this is the differential amplifier we are considering. Yeah, general differential amplifier with the current. IE and the currents are. So this is your V1 and the currents, this is your I1, and this current over here is your I2. So with this analysis over here to demonstrate the small dynamic range of V1 with respect to currents I1, I2, I3, I4, because remember we have got two differential amplifiers in parallel. The first one is transistor 1, transistor 2. The second one is transistor 3, transistor 4. So this is just analysis to show that this dynamic range for the signal V1 is very small. At 4 VT, at small VT, the current has transferred from one transistor to the other. And the analysis is shown over here. So today, this you can go over by yourself. These are the equations of the two currents. I1 is given by IEE, 1 divided by 1 plus e to the minus V1 by VT, and I2 in general is given by IEE, 1 plus e to the V1 by VT. So if you're to plot I1 for various V1, so if you have to take V1 inside this equation, if you're to take V1 is equal to VT, then you substitute it in this equation over here, equation 8, over here. You'll get I1 is 0.737 IEE. And since I1 plus I2 is always equal to IEE, the currents over here, I1, I2 always goes to IEE. Then you can get I2 just by subtracting IEE minus I1. So if the other one is 0.737 IEE, the other one will be 0.263. So 0.263 plus 0.7 will give you IEE. So you can continue plotting 2 VT, 3 VT, 4 VT. So here you get a plot of V1 versus currents I1 and currents I2. And that's how you get this curve over here. That's how you get this this curve over here. The two curves of the currents. So the current I1 is this one, current I2 is this one. So for example, when V1 is equal to 0, if we substitute in this equation over here, I1 will be IE divided by 1 plus e to the 0, which is 1. And I2 will be I2 will be IEE in divided by 1 plus e to the positive 1 by VT, but positive V1 is 0, so it will be half. So that's how you get the midpoint over here. So this is the current relationship between the voltage input to current relationship of the collectors of the two transistors. Now, knowing that the GM in our first analysis we've done so far, we've assumed that the GM of the two transistors is constant. Okay, but the GM actually is the slope of these curves. The GM is actually the slope of these curves. So towards the middle is when the slope is almost constant. Towards the edges, the slope is not constant. So the GM is not constant. So the equations we've derived so far, we've assumed that the GM of the differential amplifiers are constant, but that's not the case. So we've got to do a more accurate analysis, and we'll consider it. I'll consider this analysis to be called accurate analysis of the Gilbert's multiplier cell, i.e., we'll be assuming that the GM is not constant. So I've said over here, note, in the earlier derivation, it was assumed that the GM12, which would be equal to GM34, is IEE divided by VT. In practice, the actual value of GM is the change of I1 by V1, or change of I2 by V2, or change of I3 by V3, which is not constant. Okay, so from this section over here, from these results over here, if you plot the graph, which are plotted approximately over here, you find the only information which is missing here is if I was to put the total current is always equal to IEE. So this maximum value is IEE. So the sum of the two currents for any voltage is always equal to IEE. So the dynamic range of the signal is plus minus 4 VT, because also on this side, this is 0. This will be minus 4 VT. So the signal in the two inputs can go approximately 4 times 26 millivolts at room temperature, approximately 100 millivolts. If you put a signal beyond that, then the collector current will clip, and therefore your circuit no longer acts as a multiplier, because the voltage will not be able to change once the maximum collector current flows in any of the two transistors. So we got to come with a new scheme of how to analyze the Gilbert's multiplier. I've also said that here that to extend the linear range of the signal V1, because the linear range is less than 4 VT, we have to employ a preconditioning circuit whose value is the inverse transfer function of the voltage to current relationship at the input of Q1 and Q2, and of course also Q3 and Q4. Remember, the differential amplifiers which are fed with the signal V1 are Q1, Q2, and Q3, Q4. Okay. And to design the preconditioning circuit, we have to analyze the Gilbert's multiplier cell using Eber-Mol's relations. So that is what we are going to do now. So this is the more accurate method of obtaining the transfer function of the Gilbert's multiplier. So sometimes it's called the accurate analysis of the Gilbert's multiplier cell. So once we get the accurate transfer function, then we can design the preconditioning circuit. So let us do that. Let us get the more accurate transfer function of the Gilbert's multiplier cell. So in the notes, I've started once again with our basic Gilbert's multiplier cell, which is this one. I wanted you to see the constant current source, so I've decreased the scale a bit. So we have these transistors, Q3, Q4, Q5, Q6. These are the two parallel differential amplifiers on top. And then the bottom one here, now I'm calling it Q1, Q2. Remember in our earlier analysis, we are calling Q3 our Q1, Q4, we are calling it Q2. And this one, Q5, we're calling Q3, Q4. And then this bottom one, which is Q1 here, we're calling it Q5, Q6. But for this analysis, I'm using this nomenclature. So the first transistor here is Q3, Q4 next to it, then Q5, Q6. Then the bottom one I'm calling Q1 and Q2. So we'll analyze this circuit using the Eber-Mols current relationship between the collector currents of a transistor and the voltages of the input of the transistor. So let's look at this circuit. And for this circuit, if we apply Eber-Mols current relationship to Q1, Q3, Q4, Q5, Q1, and Q2, you'll get this relation. I've just drawn this this circuit over here. I've just drawn it so that you know when I'm using my laptop, I draw perpendicular to the screen. That's why it's a bit shaky. I don't use it as a tablet, which is flat down. So I've just drawn this sketch over here so that when you're looking at the equations over here, we can relate to the transistors. So Q3 is this one, Q4, Q5, Q6. The bottom one is Q1 and Q2. And therefore, the collector current of the bottom one is IC1. Let me see if I can write it neatly. So this is your Q1 transistor. So just sketch it again over there because the equations are close to it. So let's apply Eber-Mols current relation to transistor Q3 and Q4. Remember, the general equation for Eber-Mols current relationship is, say, IC for those of you who'll be lost, let me just go back. I know I might take a shortcut for you people, but actually I'm using these equations over here for the differential amplifier. For this setup over here, if the transistor to the left, we call it Q1, Q2. So for this circuit, if I start at the base of Q1, let's call this one Q1 and Q2. If I start at the base of Q1 over here, I drop VBE1, then I add to VB2. If I apply KVL, I'll get V1 minus VBE2, sorry, minus VBE1 plus VBE2 is equal to 0. So I'll get V1 is VB2 minus VBE1. And so from this equation over here, V1 is, I think I'm doing a mistake over here. I think when I hurry, I make a mistake. Okay, if I start from the base of Q1, I'll say V1, starting from the base V1 minus VBE1 plus VBE2 is equal to 0. So V1 is equal to V1 is equal to VBE1 minus VBE2. And we've used these equations a lot. So we can get this first equation over here that I1, let me just magnify it a bit now for you people. So you'll get I1 can be written as I01 e to the VB1 over VT divided by VT minus 1, or which is approximately I01 e to the V1 by VT, and similarly I2 is that, and therefore if you divide I1 by I2, you get equation 3, and if the transistors are matched, you get this equation over here. I1 by I2 is equal to e to the V1 over VT. And also at the emitters, we can say I1 plus I2 is always equal to IEE. Then we can solve the two simultaneous equations in I1 and I2, and we get this result that I1 will be equal to IEE all divided by 1 plus e to the minus 1 by VT, and I2 will be equal to IEE IE divided by 1 plus e to the V1 by VT. So this will be the two equations we'll be using. I've written them here. So the voltage current relationships are these two equations. These are the two equations that we'll be using. This one and this one. Where I1 is the transistor to the left, I2 is the transistor to the right, and IEE is the common current flowing at the emitters of the two. So just remember that for the first transistor, in the brackets, we have 1 plus minus V1 over VT. And for the second transistor, in the brackets, we'll have 1 plus V1 by VT. So these are the two equations we are going to be using. Okay, so now let's go and apply these equations to, let's go and apply these two equations to this circuit over here. So I1 is like our Q3 over here. It's like the collector current of Q3. I2 is like our Q4. And similarly, I1 is like our Q6 because it's connected to positive V1. And I2 is like the collector current of I5. And the IEE for Q1 and Q3 will be IC1. And the IEE of Q5 and Q6 will be our IC2. So now we can start. So that we can relate to the current. So from above mole current relations for this transistor, IC3, this is like our first transistor to the left. So we can write IC3 is equal to IC1, which is the emitter current. This is the emitter current. This is the emitter current over here. The emitter current is actually IC1. So instead of writing IEE as we did before, we use IC1. So that should be how we get this IC1 over here. All divided by 1 plus e to the minus, remember for the first transistor, it was minus V1 over Vt. Now for the next transistor, which is our Q4, we can write IC4, the collector current is IC4, is equal to the emitter current, which is IC3. Sorry, the emitter current, which is IC1, this one here, and divided by 1 plus the second current is positive, e to the positive V1 by Vt. Similarly, if we apply this to transistor number 5, so this is our transistor number 5, this one here. My sketch is very rough. Transistor number 5 is this one. So IC5 is this one, is equal to IEE, but our IEE is IC2. So it will be IC2 divided by 1 plus e to the positive V1 by Vt. And IC6, this one, is equal to IEE, but our IEE is IC2 divided by 1 plus e to the minus V1, because it's like similar to our Q1 in our earlier example, Vt. Then we repeat the same to the transistors Q1 and Q2 at the bottom over here. So for the transistor Q1, we can write IC1 is equal to now the emitter current now is IEE. The emitter current is IEE. Now for the first transistor, the exponent is negative. So for IC1 is actually equation 6 over here. Is IEE divided by 1 plus e to the minus V2 by Vt, because now the input voltage is V2. And the IC2 over here is the same as IEE divided by 1 plus e to the positive V2 by Vt. So that's how we get equations 1 to 6. Now let's substitute equation 5 and 6 in 1, 2, 3, and 4. Because equation 1, 2, 3, 4 has in the numerator IC1, IC2. Equation 3 and 4 has got in the numerator IC2 and IC3. But IC1 and IC2 are given by equation 5 and 6. So equation 1 can be rewritten. We substitute IC1 as equal to what is given here in equation 6 over here. So that's how I get 7. So what I've done is that I've written the substitution in the first bracket. So for example, the first term, IC3 is this number, equation 1 is IC1. So IC1, we look at equation 6, IC1 is IEE divided by 1 plus e to the minus V2 by Vt. Oh, I've written it second, sorry, I'll put it second. So this term over here is the same as this term over here. So I'll put it in the second. So this term here, this, sorry. So this term is actually this second term over here. The plus V1 term is on the left-hand side, is this term over here. So similarly, IC4, the first term is IC1 divided by 1 plus e to the V1 by Vt. So I put 1 plus e to the V1 by Vt on the left, this term over here. And then the IC1, I've substituted and put it on the right. All right, let's check this. IC4 again. From equation 2, IC4 is IC1. Now let's look at IC1 from equation 6. It's minus in the numerator. So actually in equation 4, I'll put it on the right-hand side. If you check carefully, IC1 is equation 6, and you can see the exponent is minus V2. So the minus V2 is here. Minus V2 is here. And the remaining part, which is 1 plus positive V1 by Vt, is on the left. Okay, so I repeat again for IC5, which is our equation 3 over here. IC5 is equation 3. So IC5, equation 3 is IC2 divided by 1 plus e to the V1 by Vt. So I substitute for IC2 from equation 5 over here. So it's IEE divided by 1 plus e to the Vt, positive V2 by Vt. So I'll put the positive V2 over here. And there, lastly, IC6. IC6 is equation 4, which is IC2 divided by 1 plus e to the minus V1 by Vt. So I substitute for IC2 from equation 5. So you'll get IEE 1 plus positive V2. So it's this term over here. Substitute this term. And then IC6 is equation 4 is IC2 divided by 1 plus e to the minus V1 by Vt. So that's the first term over here of 10. This is the first term of 10 over here. And then multiply it with IC, it was IC6. I multiply with IC2, which is equation 5, which is IEE divided by 1 plus e to the V2 by Vt, which is this term over here. So the IEE is here, and this is IE divided by 1 plus e to the V2 by Vt will give me my IC1. Okay, so I think that's the difficult part where you can make mistakes. Okay, so next, I want to consider what is known as the differential output current of the circuit. The differential output current is actually used to obtain the differential voltage. Okay, so what is the differential current? It's just, if you use this circuit over here, if you just use this circuit or even use the cleaner circuit here. So in this circuit over here, if I was to get the voltage output, so the voltage V naught, if this side is positive and this side is negative, will be equal to the drop across RL. And the drop across RL is what? It will be VCC minus I3 plus I4 or IC3 plus IC4 into RL. Minus, in the second bracket, I'll get VCC minus I4. There won't be space here, so let me just put the second bracket here. Done. Minus I4 plus so this gives you the output voltage. This will give you the output voltage. Now the output voltage can be written as V naught, can be written as the differential current into RL. If you simplify this equation, you'll get the VCCs will cancel. So you'll get a function of current and RL. So that is what is called the differential current. So the differential current times RL will give us the output voltage. Now the differential current, like from this equation over here, from this equation, if you open the brackets, is what I've done actually in the analysis. If you open these brackets, the VCCs will cancel, so you'll just get an equation in terms of the currents and RL. And I've done it, so there's no need to me waste time doing that. So the differential current at the output is given by I3. So delta is our differential current over here. It's given by I3 plus I5 minus I4 plus I6. Because if you put a bracket across these two and multiply by RL, you get the same equation as what I've just derived. You get the same exact equation as what I've derived. Okay, but this equation 11 is the equation for the differential current. Differential current times RL will give us the voltage at the output. Now, this differential current 11, I've just rewritten it this way. If you open the brackets of 11, you'll get I3 plus I5 minus I4 minus I6. And if you rearrange this, you can write this as I3 minus I6. I want it in this form, I3 minus I6. So I've just combined this I3 and this I6. And then I'll remain with I5 minus I4. But I want to put it in the form of I4 minus I5. It will still the same thing. So in this equation I'm here, you can rearrange it and put it that way, which is the same as this equation 12. So we'll need this. That's why I'm rearranging it that way. So the differential current can be written as 11, as equation 11, but we can also write it in the form of equation 12. I3 minus I6 into brackets minus I4 minus I3. 11 and 12 are just the same thing, but putting it in the form of 12 will help us simplify the equation that we want for differential current. So I'll use it in this form, the form of 12, which is I3 minus I6 minus the brackets I4 minus I5. Now, what is I3? Just remember that once we get the differential current, we can get the output voltage, because differential current times the resistance RL gives us the output. So let's substitute for I3, I6, I4, I5 from the equations we just derived. So I3, let's go back to the equation. I3 is our equation 7 over here. I3 can be written as IEE all divided by 1 plus e to the minus V1 by Vt, close the brackets, into 1 plus e to the minus V2 by Vt. So you can check it. The first term is minus, second term is minus. Let's check again. I3, the first term, the numerator is minus V1 minus V2. Okay, and here you have it here, minus V1 minus V2. Minus I6. So I6, once again, we can just go back. Equation 10 is I6, it's IEE divided by 1 plus minus V1 into 1 plus positive V2. Minus V1, positive V2. And then there's a minus sign, it's not very clear. There's a minus sign over here. Then we start again, I4 minus I5. So I4 is here. I4 is equation 8. So it's IEE, 1 plus positive V1, 1 plus minus V2. So positive 1 minus V2. So it's this term over here, positive V1 minus V2. Then minus I5. So I5 is here. Equation 9 is IEE, 1 plus positive V1, 1 plus positive V2. So we have it over here. IEE, 1 plus positive V1, 1 plus positive V2. Now there's so many variables over here. So to make sure we don't do a mistake, let's use the substitution that let V1 over Vt equals X and let V2 over Vt equals to Y, so that the equations look a bit simpler for us to, so don't make mistakes with the too many variables. So let me put it here so we can see all the equations. So for this first part over here, In the numerator, 1 plus e to the minus v1 by vt. v1 is x, so it's 1 plus minus x, 1 plus minus y, 1 plus e to the minus y. So it's this term over here. Similarly, for this term over here, we get, instead of minus 1 by vt, minus x, v2 by vt, positive y. Then for this term over here, we get positive x over here, which is this one. Then for here, we get minus y, get this one. And for this last term, you get positive x, and then you get positive y. So you get this term over here. So that's how we get equation 14. We get in the variables so that we don't make mistakes. Okay, now it's time to simplify 14. Now I've just rewritten 14 as 15 in one line. I've just written equation 14 as 15, but all in one long line over here. Then we look for the common terms. So 1 plus e to the minus x over here is common to this one, 1 plus e to the minus x. So I've written 2 lines below it to know that these two are common factors. Then on this side, 1 plus e to the positive x is also common to 1 plus e to the positive x over here. So we can simplify this first big bracket here before the minus sign by taking 1 plus e to the x common. All right, so I pulled this one. Sorry, 1 plus e to the minus x common. So I've taken this one, this term over there, and brought it here. What am I doing? Sorry. Where did it come out from there? I've gotten this term over here and brought it here. So this term, this common term which was here and here, I brought it outside, and then I'll get this term over here. 1 divided by 1 plus e to the minus y is this term. And then minus 1 plus e to the positive y is here. When I close up brackets, minus, then this term which is common in the second bracket, 1 plus e to the x, 1 plus e to the x, I've brought it over here. And then I get an inner bracket to take care of this term over here, 1 plus e to the minus y, this one. E to the minus y is this one, then 1 plus e to the minus, to the positive y is this term over here. So now we are just simplifying. You can forget all these things that I've written over here with the pen. They just concentrate on the typed notes. So now once again, in equation 16, we look for the common terms. So if you look at this term, 1 plus e to the minus y minus 1 plus e to the power y, this term is the same as this term over here. This minus y, the same as this minus y. Positive e to the positive y, the same as this one. So I can get this term over here and this term over here common. So I'll put it over here. So I get 1 divided by 1 plus e to the minus y minus 1 plus e to the positive y, which was common in this term and this term, into this term over here, 1 divided by 1 plus e to the minus x, which is this first term. And then this term over here, 1 divided by 1 plus e to the x, which is this term. So that is how I get equation 17. That is how I get equation 17. It seems like you lost the internet connection or what? Can you people hear me? Anybody switch on your mic?
Yes.
But how come, can you see the presentation?
Yes.
How come my student computer, I can't see the presentation in my student computer? It's my feedback system. Okay, let me use the same network for both. Do you people have a class after this? CR? CR? Just switch on your mic.
Yes.
So we stop over here. You want us to stop or we continue? I've just almost finished. My student computer is giving me a problem.
We can continue a few minutes.
We can continue a few minutes, okay. Let me just make my student computer to work. It gives me the feedback that the network is on. It's asking me to join. Okay, at least now I'm happy my student computer is on, but we're on the same network. Normally I don't put the student computer and my main computer on the same network. Okay. So we had simplified 16 to get 17. Now we've got to simplify 17, equation 17. Now to simplify 17, I say just forget what I've written with my pen over here. Let's just concentrate on the class notes over here. Now to simplify 17, let's consider this function over here, 1 divided by 1 plus e to the x, which I can write it in this form, 1 divided by 1 plus e to the minus x. Then I multiply numerator with e to the x, denominator by e to the x. So the numerator will become e to the x, and the denominator will come to e to the x and e to the 0. 1 plus e to the x. So 1 divided by 1 plus e to the minus x can be written as e to the x divided by 1 plus e to the positive x. So let's substitute 18. Let's substitute 18, this result of 18, in one of the terms of 7. In one of the terms of 17. So if you look at 17, this part of 17 over here, where we got 1 divided by 1 plus e to the minus x, minus 1 divided by 1 plus e to the x. Now this term over here, on the left-hand side, 1 plus e to the minus x, I can substitute it with this one, which is the result of 18. Then I'll get equation 19 on the left-hand side. So this term over here is the same as this term. And this second term, minus 1 divided by 1 plus e to the x is this term over here. So if I make 1 plus e to the power x to be my common denominator, then the first term will be e to the x, the second term will be minus 1, and I can rearrange the numerator as minus into brackets 1 minus e to the x, all divided by 1 plus e to the positive x. So this term over here is the same as this term over here. Now similarly, I can apply to this term over here, 1 divided by 1 plus e to the minus y. I'll multiply numerator, denominator by the e to the x. And let me see if I've done it down here. Okay, I've done it here. So I've said similarly, 1 divided by 1 plus e to the minus y. Okay, I've just taken a shortcut. Can be written as e to the y divided by 1 plus e to the y. So I've not done everything the way I did it. I did it over here for the x. All you have to do is multiply numerator. So if it was e to the y, I multiply numerator by e to the y, and this was e to the y, then you get e to the y divided by 1 plus e to the y. So for this term over here of 17, I've just concluded the result by just considering to be similar to this right-hand side of 18, only that I substitute instead of x, I use y. Then then the whole bracket, which is 1 divided by 1 plus e to the minus y minus 1 plus e to the positive y becomes similar to this expression which we did for x, and we'll get minus into brackets 1 minus e to the y, all divided by 1 plus e to the positive y. So, and with that one, I've done it over here. So I've done the 2 steps, and we've gotten that term to be minus 1 minus e to the y divided by 1 plus e to the x. So these are 2 important results to remember. We're going to use them later on. But now, let's consider tan hyperbolic x. Now, tan hyperbolic x is defined as sine hyperbolic x divided by cos hyperbolic x. But we know that tan hyperbolic x is e to the x minus e to the minus x divided by 2. And cos hyperbolic x is e to the x plus e to the minus x divided by 2. And if you simplify this, you just get the numerator, e to the x minus e to the x, because the 2's will cancel, divided by e to the x plus e to the minus x. Then to simplify it, what I'm going to do, I'll multiply the numerator, denominator, by e to the positive x. And if you multiply in the numerator e to the x into the top part, you'll get e to the positive 2x minus 1, because this term e to the minus x into e to the minus x will be e to the 0, which is the same as 1. And in the denominator, we are going to get e to the 2x plus 1 again. So you get this equation over here. And then I'll just rearrange it. The numerator can be written as minus into brackets 1 plus e to the 2x. The denominator, I've just started with putting 1 on the left-hand side. And therefore, tan hyperbolic x can be written as equation 21 here, or in equation form, tan hyperbolic x is minus into brackets 1 plus e to the 2x, because the brackets divided by 1 plus e to the positive x, positive 2x. And since I'm going to use it in this form, I'll use another variable, m. So tan hyperbolic m divided by 2. We just substitute x in equation 21 for m by 2. So tan hyperbolic m by 2, I could have used p by 2, any other variable, can be written as minus into brackets 1 plus e to the m, all divided by 1 plus e to the m. So now we finished all the difficult part. Now let's look at, so this equation 22 is very important because we're going to use it. Now, the differential current, which is all these things, this is the differential current, equation 17. Remember, this was equation 17. The differential current is IEE into all this bracket, equation 17, and we've simplified all this bracket to be the first term of the bracket is in terms of y, it is 1 minus e to the y, all divided by 1 plus e to the y, times the second term is minus 1 minus e to the x, 1 plus e to the x. All right, remember this was, let's start, just in case you forgot. This was this bracket of 17 in terms of x over here. This term, we simplified it to this part. And this term over here, in terms of y, we simplified it to this term over here. So you've got two terms which are similar, only the exponents are different. One is y, one is x. So since they multiply to one another, this term times this term, you get this, the first term in terms of y, times the second term, which is in terms of x. And we found out what this term is, what this term is. So this first term is identical to our equation 22, only that instead of m, we have y. So it's, the first term will be y by 2. And the second term will be x by 2. So the differential current Delta I naught is I triple E tan hyperbolic y by 2 into tan hyperbolic x by 2. Now I'll leave for you to do this, but the output is just the differential current times RL, which is equation 25 over here. So equation 24 times RL will give us differential current. So to get the sign, you got to substitute all this. So the output voltage is just minus RL I triple E into tan hyperbolic V2. If I substitute back my variables, Y was our V2 by Vt. So it's V2 over 2 Vt, because it is Y by 2, into the first term, which is tan hyperbolic x by 2, which is V1 by 2 Vt. So equation 1 is the accurate expression for the input-output relationship of the Gilbert's multiplier. Now in the next class, we'll analyze this equation 25 in more detail. Because there are 3 cases that exist. So I'll stop over there. But just remember that this is the exact expression for the response of the Gilbert circuit. In the next class, we'll consider these 3 categories of how the output changes for various values of V1 and V2. So I'll stop over there. You can go and do this 24 to 25. They're just obtaining the output. Remember, the output is just the drop across the first resistor minus the drop across the second resistor. And I don't want to waste time on that one. So I hope that is okay. So we can stop over there for today. So in the next class, we'll consider these 3 possible outcomes, depending on the values, the magnitudes of V1 and V2. And then go to the preconditioning circuit. Because from 25, we know now the exact expression of how the output varies as a function of V1 and V2. So it will give us a way of how to design the preconditioning circuit. So from that equation, you can see it's not a linear. Before we are saying V0 is some K1, V1, V2. But accurately now we can see that it's not very linear. It's not a simple K. It's tan hyperbolic KV1 into tan hyperbolic some scalar V2. So thank you. I'll stop over there for today. Unless there's any questions. Okay, if there's no questions, then I'll stop over there.